Welcome to Investigation 1.3, and in this investigation, our focus was on growth factors and looking at how various plans or various equations can change how growth factors work. In this investigation, we were initially looking at what the peasant's plan was in the previous investigation, where essentially everything doubled and you had a normal chessboard that was 64 squares. And by the end, you would realize that the king would bankrupt his kingdom if he continued to pay out the peasant the way he was. He'd essentially end up being multiples of trillions of dollars in debt. However, you also see that the queen's plan and the king's plan, and even the king's advisor's plan eventually, wouldn't actually be much better. The only one that would be good would be the advisor's plan, which was actually a linear situation. Regardless, in this investigation, we are looking at growth patterns. And so our focus question for this investigation is, how does the growth pattern for an exponential function show up in a table, graph, or equation that represents an S, represents a function? So we're looking at how things will progress with tables, graphs, and equations. So let's move on and get a couple of vocab terms. So words worth knowing. Our first word worth knowing is exponential growth. Exponential growth is essentially what we've been working with. Typically in exponential growth, we'll see a graph that starts out kind of slow and then starts to double or triple or whatever it may be as quickly as possible. What's interesting about exponential growth is it specifically will grow at a constant rate, but it'll be a timesing situation instead of an adding situation like with linear growth. So it specifically will grow at a constant rate based on multiplication. And that's kind of fun to look at. So that multiplication that we see is that constant growth is all based on a growth factor. It is a fixed number in an exponential growth function. So in the king's Ruba's plan, for the peasant's plan, the growth factor was 2. We'd end up with y is equal to 2x minus 1, and that described the peasant's plan. So the growth factor was this 2. Exponential growth situations, you'll always find that there's an exponent involved, and that exponent happens to be the variable that will change. We've also looked at this other equation, y is equal to 2 to the x power, where 2 again is that growth factor, and then that exponent is that how everything becomes exponentially bigger, because that will change. That is our variable. Moving on, we also have the concept of exponential functions. And exponential functions are this same idea where we have y is equal to 2x or y is equal to 2x minus 1, but a function indicates that for every input we have, for every x value, we will find only one y value. So essentially, if we put an x value in, say 2, we will have one and only one y value as an output. So the input, that independent variable, maybe the number of cuts of the ballots, maybe the number of squares on the chessboard, that is something we can control. We can say, yes, we are going to put checkers on that spot, but the number of checkers is all dependent upon that function that you're dealing with and its result, its dependent variable, the number of checkers that's on that spot is the dependent variable. And so those exponential functions, you'll have one and only one x value to create one y value. So it has a direct relationship. You'll never find an x value gets put in and you end up with two outputs. We'll never make 3 cuts and find that we have 2 different numbers of ballots that's created. That will not happen in this case because we are being very careful with what we're doing, and that would mean that our function machine, if you guys remember doing that with thinking with mathematical models, our function machine is not broken. One ingredient comes in, one ingredient comes out. So if you guys remember, we would put like ground beef in and out would come a hamburger. We wouldn't put ground beef in and get a hamburger and a goose or anything like that. We don't have a broken function machine, so that's not happening. So let's move on. We're going to be looking at independent versus dependent variables. So when we look at independent versus dependent variables, we are looking at that whole concept of cuts or squares versus the number of pieces of paper we get, or the number of ballots we get versus the number of rubas on a square. So if we looked at independent variables with things that we've already been playing with, sorry, that was crazy. If we look at our independent variables versus our dependent variables, we can see that we did cuts of paper, and we'd have the outcome of ballots that were made. We also had squares on a chessboard, and out would come the number of rubas, this made-up currency, that would developed from that. So essentially our independent variable was the cuts of papers or the squares, and our dependent variable were the ballots or the rubas. So if we're thinking about independent versus dependent, if we're looking at a graph, remember that our independent variable goes across the x-axis and our y-axis stuff will be our dependent variable. So essentially the squares would be here, and our rubas would be showing here. So we would eventually see that. If you ever do it incorrectly, you'll end up with a graph that looks potentially like this, and we don't want that. We want to be able to see that growth, and we don't necessarily want to see a decline. Okay, so this would be bad. Now, let's move on. Let's look at comparing some exponential growth. So we have a couple of equations that we're going to compare to begin with. We have equation 1. Our first square has 1 checker. Our second square has 2 checkers. Our third square has 4, and so on. So what sort of pattern are we seeing? What sort of growth factor are we seeing? Well, I see a doubling here. And if I see a doubling, that means our growth factor, I'm going to put GF for an abbreviation, is equal to 2. In our second equation, we have the first square has 1 checker, the second square has 3 checkers, our third square has 9 checkers, and so on. So in this one, I see a tripling. And therefore, our growth factor will be 3. So that means we will have 2 different equations. So let's figure this out based on a couple of chessboards or a couple of tic-tac-toe boards. So I'm going to minimize my pen here. So for this first one, our first square had 1 checker, our second square had 2 checkers, our third square had 4 checkers, and so on. So we see that doubling happen. So if there's a doubling, our fourth square will have 8, our next square will have 16, then we have 32, 64, 128, and 256. So that's how everything will grow. For our next equation, we have our first square, which is 1, our second square, which is 3, our next square is 9, and 9 tripled is 27. 27 tripled is 81. After that, we need to continue, so I'm going to play with a calculator, so if I take a little bit, I'm just doing a little bit of math. Our sixth square is 243, our next square is 729, our eighth square is 2,187, and our ninth square is going to be hard to write in. We have 6,561. So we can see everything start to develop with that. So if we're looking at just this sort of visual, we can see clearly that a tripling is much more lucrative, more money potentially. If these were actual coins or something like that, we'd definitely be growing fast money. That would be pretty sweet. If we had a tripling situation. By the way, no bank account actually does that. It doesn't actually happen. Usually you have interest rates that are like a percentage of a percentage. Regardless, let's play around and put these values into a table. So we just have squares 1 through 8, so that's all we're going to add. So our first equation, we had 1, our second we had 2, then 4, then 8, then 16, 32, 64, and 128. I'm going to pause this and fill this out for the rest of it, and yeah, we'll continue from there. So a little bit of math magic for you. Something just suddenly appeared. We have our next little bit that has been filled out for this. So now we can really see for each square we're seeing a doubling or a tripling. So let's really quick talk about how these equations or how these situations would turn into equations. If we look at equation number 1, we could say that we could write, we have y is equal to, we have a growth factor of 2, but remember our first square is showing a 1 there. So how do we represent that? We show our x, which is our variable. We need that to be in our exponent, otherwise we're not showing an exponential function, and we're going to subtract 1 from it. Because we know that if we put 1 into our exponent, into that x, if we did 2 to the, not 2 to the 0 power, if we said 2 to the first power minus 1, we'd end up with 2 to the 0 power, which is equal to 1, and that represents that first square. And from there, we could also say 2 to the first power, which would be our next one. 2 to the second minus 1 would equal 2 to the first power. And we get 2 and so on, and we'd start to see that doubling. As well, we need to create an equation for our other one. So we have this tripling effect. So there's our growth factor of 3. And we have our exponent, which is a variable. And we need to modify that variable so that way we have that 1 showing up in our first square. So we're going to, again, subtract 1 from our exponent. Another way that we can write these is maybe having it be y is equal to 1/2 times 2 to the x power, if that makes more sense to you, or y is equal to 1/3 times 3 to the x. Both of those are also valid equations that you could create. However, I'm not going to explain those here. If you have, or if you're trying to create those types of equations, I'd be happy to answer any questions on a one-on-one basis. I'd like to see you create these equations here just because they make a little bit more sense personally to me. That doesn't mean they make more sense to you. So if you're making the other equations, I can still explain them and I can still talk about them if you'd like me to. So now, after we've compared these equations and after we've put them into a table, we can see how things double times 2 versus triple times 3. We can also see that the results are drastically different as we get into the higher numbers of squares. 128 is much different than 2,187. But we can also create a graph so we can see how much these two things are changing in comparison to one another. So I am going to create this graph. I'm going to make a scale. So bear with me for a second. Some math magic is going to happen. So we're going to put a little bit of, I created a scale, and our scale for the checkers that we have going on is going up by 50s, and our scale for the squares is just going up simply by 1s because that's an easy scale for that. Now, the scale for the checkers is always never going to be enough. You just got to deal with it. It's really difficult to see how things change at the beginning, but you start to see the drastic difference as it keeps going and it keeps increasing. But one thing that's really important is to understand that even with that situation, you still might not be able to be super accurate with your graph. Understand that a computerized graph or a graph on a calculator is going to be much more accurate with this sort of thing. So I'm going to graph these points, and as I graph these points, I'm going to eventually pause it and make some math magic. But we start out with at the first square for this first equation at 1, so nothing really changes. At 2, it's at 2, so that's really hard to show. 3, it's at 4, so again, really hard to show. 4, it's at 8, again, very hard to show. At 5, it starts to get a little bit more easier. We're at 16. At 6, we're at 32, starting to get get a bit easier. At 7, we're at 64. And at 8, we're at 128. So we're starting to see a bit of a slope being created. Let's graph this other one. Again, at 1, we're at 1. At 2, we're at 3. Still very little bit of a change. At 3, we're at 9. Again, still very little change. At 4, we're starting to see some more change, 27. At 5, we're at 81. Much bigger dramatic change. At 6, we're at 243. Huge change. At 7, we're already at 729, which is way off our graph. It's way up in the boonies. So we can now graph as much as we possibly can. We're going to see a huge dramatic change. So you can start to see how a tripling effect is dramatically, sorry, very poor handwriting today, different than a doubling effect. Even though a doubling effect is pretty awesome, tripling effect is way more awesome. However, in our situations that we have going on in Investigation 1.3, there are limitations to our chessboards. However, we can still see that a tripling effect is still fairly astronomically substantial. I hope this helps you see how tabular methods, equations, and looking at graphs, you can start to really see how these exponential functions are different, especially with different growth factors involved. A doubling is very nice for a growth, but at the same time, a tripling is even more substantial. You can imagine a quadrupling. If we had a quadrupling here, we'd maybe see something even more dramatic. So looking at those sort of things is kind of fun. This is where math gets to be cool. So work on your homework, see how it goes. I'm going to go back to the very beginning of this investigation screen. Play around with that homework. If you please come to class with any sort of questions you may have, and I will talk to you later. Bye.